All right, here is lecture 18. This is the second half of the class ME 3501. And I will first start by briefly going over chapter 7, exergy, which is something that we have to have talked about. I have a few graphs about it. So exergy is a concept, sort of thermoeconomic concept. Essentially, what you look at is here is your system, which has a temperature, a pressure, an entropy, an internal energy, kinetic and potential energy. And around it, you draw yourself a very, very, very large control volume that you call the surroundings, which has a temperature T0, pressure P0, entropy S0, internal energy S0. Now, this system, S and U, can exchange heat and work and everything else with the surroundings. But the surroundings are picked to be large enough that they do not exchange heat with their boundary. However, they can exchange work. That work would be WC. So that if you then write the energy balance for the whole, the change in energy over the control volume is in fact, over this control volume, is in fact entirely the work. Now, this change in energy is the work, can be spelled out following the second law. This is simply the balance equation. So that work is internal energy, kinetic potential energy, minus the work on the surroundings. And then the pressure volume of the small volume minus that of the surroundings, entropy minus that of the surroundings, and then, of course, work lost to irreversibilities is here. This maximum, you can rename that to be then the exergy. And you can regroup it as to changes in internal energy minus that of the control, that of the control volume minus that of the surroundings, which is major macroscopic control volume. Volume here, entropy here, kinetic and potential energy. So why is that important? Well, in essence, you recognize essentially the PDV equations because you have energy, you have PDV, and you have the TdS equations here. So it's a definition, it's another equation of state that you can define this way. And you can then give an energy analysis on this. And in fact, it will give you really the same conclusions that you would derive if you just use the first and the second principle. And that conclusion is that your system is that much more economical and that much more efficient as you can minimize the irreversibilities. And it also gives you an idea for the value of energy. Basically, heat has a higher value when it is supplied at a higher temperature. That's the bottom line. And of course, these are knowledges that you can get from second principle, and you can get to this conclusion simply by looking at the Carnot efficiency, because 1 minus T cold over T hot is maximized when T hot is very hot. So that means heat at a high temperature has more value than heat delivered to your system at a low temperature. That's the essence of chapter 7. And let me now move on to chapter 8, which are the vapor power cycles. So the rest of this class really is going to go in detail over 4 types of cycles: vapor power cycles, then gas-based power cycles. We'll have the Brayton cycle, which are jet engines, the Rankine, the Otto and the diesel cycles, which are the piston engines typically used in cars and boats. And then we'll have refrigeration. So let's start with vapor power cycles. So what are vapor power systems? Introduction. And then explain the ideal Rankine cycle, which is the prototype, the paradigm for the vapor power cycle. We will go over the performance parameters for this Rankine cycle, thermal efficiency, and then a new concept, the back work ratio, and explain what useful that is. Effects of boiler and condenser pressures on these cycles, and Rankine cycles with the reversibilities. That will be this lecture and the coming lecture. So why are vapor power compression cycles, vapor power cycles so important? Well, first of all, it is actually the origin of the entire science of thermodynamics. It has a very ancient history because the vapor power cycles were the very first machine that was used in practice is the Newcomen cycle, which is this bizarre thing here. I'll show you a few demonstrations of it. That was used as a pump in a coal mine. So here is the piston that goes up and down, and this is where the device pumps water out of the coal mine. And there is a boiler, there's a chimney. So this is exactly like what we will see in details. Of course, this cycle has dominated mechanical engineering between 1911, these piston-based engines, and the 1940s, where you had steam locomotives that look like this. This is all very nice and romantic. I have put together a PowerPoint presentation on heat engines over the centuries on Kármán, and if you want to see a few of these machines or prototypes of these machines in operation on little videos, you can enjoy that. But of course, this is not going to go on the exam. Why is that important? It's because these engines really powered the Industrial Revolution, historically speaking. They are also the origin of the mechanical engineering departments in practically all universities. This is what we taught. This is one of the first things we taught. Now, the real importance that we have today, you can find again in this US energy flow. That was 2002, so that these things are not just quadrillion BTUs, but also percentages, because if you sum the sources of energy for the US in 2002, you come up with 100 quadrillion BTUs, which means, coincidentally, these numbers are percentages. So coal in 2002 constituted 22% of the input of energy to our entire economy. Petroleum and natural gas, petroleum and liquefied natural gas, 14, of which 24 was imported. Natural gas, 20% here. Hydroelectric, 2.8, 2.6. Nuclear was 2.8. And this then gets converted into transportation engines or into electric power sectors into useful electricity or motive power, if you're looking at transportation. Well, the vapor power cycles are this. They are the thing that makes that powers the electric power sector. In other words, it powers the outlets in this room and the electrical power. You can see immediately that the distributed electricity is 11.9% of the total energy, whereas the heat losses, the rejected heat, which is heat losses, are 26%. So you can right away see that the general efficiency of these things is 12 out of 38, so it's on the order of 30–40%. That is what we will study in this chapter. Now, these are power generation cycles in general, and they're just like so are gas turbines and IC internal combustion engines. But these are cycles that operate based on a phase-changing working fluid by alternatively vaporizing it and condensing it. That is quite important, because if you look at your thermodynamic tables, at your steam tables, going from a liquid to a vapor implies a very high change in entropy, in enthalpy or in internal energy, much more so than heating up a gas or heating up a fluid. Going from fluid to gas takes a lot of energy. So it takes a lot of energy and it gives a lot of energy, which means that these things are actually quite compact. They have a lot of power per kilogram of material that we're going to pass through these cycles. They are typically used for the large power plants and stationary power generation. Now, the source of heat, these are cycles. So you have a QC in, a QC out, and a Q hot in, and you do work out. Where does that Q hot in come from? Well, most of the time, it comes from external combustion of conventional fuels, coal, biomasses, municipal waste. The heat can also come from nuclear or from solar. So here is your classic power station. You can see that there are, these are the cooling water towers, cooling towers for cooling the water. And they're, well, we'll go into details. over what we have. So a vapor power plant typically will have a boiler where you have fuel, air. The fuel could simply be nuclear, for example, in which case you don't need air. And you're going to heat up water until you have steam here. You send that steam into a turbine. The turbine does work out that then drives an electric generator, which gives you voltages that you find out on the outlets in this room. The rest of the steam comes out of the turbine, goes to a condenser, which is actually where the heat will go out. This is where the heat goes in, hot side heat in, cold side heat out. And then the water is condensed, so it's solid water here. It goes through a pump, which increases its pressure again, and then it goes through the combustion. Now, the source of cold water, the source of cold in the condenser, is typically a cooling tower. So in which case you have a second circle, a second circuit with water. Water is pumped here. This is cooling. Water is pumped here. Goes through a heat exchanger. It takes the heat out of the water that comes from the turbine, and it puts that heat in the heat exchanger, which is then sent to the cooling tower where it's evaporated, and the heat of evaporation of the cooling water, which makes the steam, also lowers the temperature so that it can be pumped back in. Finally, there is a boiler. In the boiler, you have the water which we described, and you have the fuel that goes in. In the case of a combustion, you have fuel and air. This burns, and the results of the combustion goes up the smokestack. So this is your classic coal-powered plant. You have a stack of coal stored outside. You have the boiler, which is really the vapor, the steam generator. I'll tell you why in a minute. Is here. The gases go up, the flue gases go out the chimney, and then the water is here. Goes through a set of heat exchangers and is transformed into steam. The steam is sent into the turbine, which in turn drives the generators, and then it goes into the condenser. The condenser is a really large thing. Here is the river, pumps water in and pumps the water back into the river. This is one of the reasons why many of these plants are located along the rivers, the Ohio River, or along the lakes. It's the need for cooling. Steam generators, this thing, are not small for these power plants. They look like that under construction here. Now, typically in the US, coal plants still make about 60% of the US energy production. We are in the process of replacing coal, which creates a lot of CO2, with natural gas, where you burn CH4 essentially, so that you burn a lot of hydrogen along with the natural gas, and you emit less CO2, CO2 being a greenhouse gas, of course. But in Ohio, coal-powered plants are totally dominant because Ohio produces coal, and so that is highly protected. Typical thermal efficiency is 40 to 45%. Most plants are very, very old. Some plants are 80 years old. I don't know of any that's 100 years old. The more modern plants, of course, have better efficiencies than the older plants, but we're still stuck with a lot of old plants. These are always large plants for stationary electricity generation. Now, other sources of fuel can be used. Classically, waste heat from municipal waste can be burned. So it's accumulated here. The scale is given by the truck there. And that is sent here into your power generator. So this is your boiler and your steam generator. Now, of course, the flue gases of this require very extensive treatment because basically they stink. Another source of heat is nuclear power. So in a nuclear power plant, well, this one's French, but that's okay. In a nuclear power plant, the source of heat are rods of uranium, enriched uranium, which are here, and which then are simply going to go through heat exchange. Well, so the cooling of the uranium rods goes through a first cycle, the heat exchange cycle, which then goes to a second heat exchange cycle. That is the cycle that heats up the water, creates steam, and creates superheated steam that then sends through the turbines. A third source of heat are solar thermal plants. So in the solar thermal plants, the steam generator is here. It's here. What you do is you concentrate a large number of mirrors to heat up water in this tower. So this is the focal point of all these mirrors. That is where the high temperature is reached. And then this temperature is stored temporarily in salt storage tanks. So you use salt, like table salt, sodium chloride, heat it up to 565 degrees C using solar power, and then it's stored so that it can buffer changes in the insolation and the amount of sunlight that you heat this up with. This molten salt is then used in a heat exchanger to generate steam in the steam generator. That's here. All right. So let's now go in detail in the Rankine cycle, the basic theoretical cycle that underlies all these power generation cycles. So we have step 1 to 2. So in 1, you have steam. In step 1 to 2, you send that steam in the turbine, and you will assume that you have an isentropic expansion in the turbine, starting from a point with a high enthalpy, high pressure, high temperature, and ending in a point with a much lower enthalpy. And so at first, we're going to simply assume that this is an isentropic transformation. As you know very well, there is no such thing. There will be a finite isentropic efficiency to the turbine. That was on your midterm exam question. But we will deal with that as corrections later when we deal with real Rankine cycles. So this turbine then gives you work out. Okay, this steam is here, let's say still steam, but at a lower pressure, at lower temperature. And that steam is then converted into water, to liquid water, so here water vapor to liquid water, through the condenser. The condenser extracts heat from it to condense the water. So 2 to 3, heat transfer from the fluid to the cooling water. Water vapor mixture becomes saturated water. All right. Now this is a high pressure point, and this is a low pressure point, and this is another low pressure point. If we're going to get that water heated up and back into the turbine, first thing we have to do is we have to compress it so that the pressure here be the same as the pressure there. So we go 3 to 4. Step 3 to 4 is water is pumped into the boiler at the boiler pressure, which is going to be the same as the pressure here, because this is just a heat exchanger, and we will neglect friction in the heat exchanger, so pressure out equals pressure in. But here we have water. So the work that this pump will take to pump the water from 3 to 4 will be actually quite small compared to the work that you get out of the turbine, because here you are working with the gas, so PdV is large because dV is large, and here you work with the liquid, so PdV is small because dV is small. The pressure change is large, but the dV is small. So work in will be much smaller than work out, and in fact, the price you pay, the work in over work out, that is the back pressure ratio. That is the amount of work you have to reinvest, the amount of work that you got that you have to reinvest to make the whole cycle work. Now, finally, we have 4 to 1. This should have been a 1. That is heat transfer to the water from the boiler. Now, that heat transfer does two things. First, it heats the water, and then second, it makes steam. All right. So let's look at this on a TS diagram. Here it is on a PV diagram, but by now the PV diagram has sort of become too hard to use because all these isotherms become curved. If we go to a TS diagram, we have this first isentropic expansion in the turbine from saturated steam to some condenser pressure where you have a certain amount of quality to your steam. This being isentropic, it's vertical, so that gets you right in the middle of the vapor dome. Point number 2, you have to determine, of course, X2 to get U2 or H2. Now, 2 to 3 is the heat transfer in the from the working fluid to the cooling water. So this is basically QC out, goes from 2 to 3. In this Rankine cycle, idealized Rankine cycle, this is an isothermal transformation at constant pressure inside the vapor dome. So we simply have a condensation, and we go from a finite quality of the steam to saturated liquid, number 3. The pump now, the pump is going to increase the pressure from a low pressure to a very high pressure, in fact, the same pressure as we had here, so that these curves are isobars. But that doesn't do much work on the one hand, and also it doesn't increase the temperature all that much because you're compressing an incompressible fluid. Not just increasing pressure, but you have very little change in volume and also very little change in temperature. So that's point number 4. And then we're going back from 4 to 1. Well, this happens in 2 steps. So this is the work of the steam generator, the boiler. The first thing it has to do is go from 4 to point A. 4 to point A, you simply heat up the high pressure liquid, the pressurized water, until a point where that water becomes a saturated liquid. At that point, any heat that you add to your system is going to bring you from A to 1 by simply boiling the water, by going from liquid to vapor water. And so you go from saturated liquid to saturated vapor. That is the Rankine cycle. Now, let's analyze the Rankine cycle in some detail. So let's start again at point number 1. And we go from 1 to 2 as an isentropic transformational turbine. So let's assume that we have no heat loss. Let's then assume that we have no change in velocity. The flow rate of the water is low enough. The plant is all at equal levels, so there are no changes in potential energy. So in this turbine, the work of the turbine per mass flow rate of your fluid is simply the change in enthalpy between 1 and 2. That is this. Okay, 2 to 3, we have heat transfer from the fluid to the cooling water. Well, now there is no work here, it's a heat exchanger, so the heat out of the system divided by the mass flow rate is H2 minus H3. That is this one. Then we pump the water from 3 to 4. That pump takes in work. What amount of work? W dot over M dot is H4 minus H3. And then we have heat transfer from 4 back to 1, which is 5, not 1, and that is actually heat in. So the heat in serves to change the enthalpy from 4 to 1. Notice that when we have written these 4 equations, we have actually thrown the sign conventions out of the window. What we have done is we consider that the work of the turbine is work out, and it is positive because of the arrow that we have in this little figure. H1 being higher than H2, this is a positive number. Q out from 2 to 3, this has more enthalpy than this. This is also a positive Q. That Q out comes with its arrow drawn as in the figure here. The work that the pump takes has its arrow drawn inward. So again, it will be positive because indeed H4 is going to be higher than H3. And then the heat that goes into the heat exchanger in the boiler, the steam generator, is from 4 to 1, but the way we have written it here, Q in is positive because H1 is higher than H4. So in these cycles, in fact, just like we did when we introduced cycles, the numbers are all going to be positive, and we are going to change the signs in the energy conservation equation. So the signs are going to be determined by the direction of the arrows for work out, for heat out, for work in, and for heat in. Always have your schematic diagram, always write your arrows so we know which signs we're going to be using. But by convention in Chapter 8, these signs will be all positive. And that's it for today.